Great. Yeah, so 1 o'clock here, so I think we get started. People will probably be trickling in here towards the beginning, but thanks everybody for joining. We're here at Sodick, we're real excited to have Pat Haney here from a good partner of ours in MTD Micromolding. This is a topic that we've gotten a lot of questions on throughout the years, particularly with some of the crazy intricate and small molding that goes on at this facility and other Sodick customers. So real excited to have Pat here. Should be a great presentation. Just to give you a little background, as I mentioned, MTD has been a great partner of Sodick's on the injection molding side for a long time now. And doing some pretty incredible things in terms of kind of testing the limits of what our machines can do, what any machine can do, what's even possible in the injection molding world. So again, real excited to have Pat here. Pat is a Penn State grad with a background in plastics engineering and kind of a focus on the material science side of things as well. So again, very excited to have him here. So give you a taste too. Upcoming, we've got about every 2 weeks we've done one of our Sodick and Friends webinar, part of a webinar series here. So we've got coming up here another presentation from a good partner of ours in Extol on laser welding, another molder in isometric micromolding for kind of a different take on things, and I believe some material suppliers, some more auxiliary equipment, and some more white paper, more technical scientific molding type stuff as well coming up. So stay tuned for that. And yeah, I guess a real quick thanks. If you see kind of all of us up top here, my name's Bennett Howard. Probably should have started with that, but I'm just doing the intro here. Len Hampton is our national sales manager at Sodick. That handsome gentleman up there. And Weston Harbaugh will be kind of our guide here as we pass off to Pat, and he'll be responsible for some of the Q&A, and he'll explain that here in a second. But Weston covers the East Coast for us for Sodick.
Yeah, thanks, Bennett. Thanks for the introduction.
Yeah.
Thanks, everybody, for joining. Just want to say a few words, but these are real important to us, getting everybody engaged. Looks like we have another fantastic crowd out there. Patrick, thank you for your presentation. That being said, Weston kind of goes through some of the rules and whatnot and kicks things off. So Weston, you'll be the host and mediator throughout the Patrick's presentation. And maybe go ahead, Weston. Thank you.
Thanks. Yeah, as Len mentioned, a few things here, rules-wise or suggestion-wise, right? Pat's going to speak for about 45, 50 minutes here, and then we'll go into a Q&A section at the end of that. So instead of interrupting him in the middle of his presentation, if I can get everyone to send your questions in through the Q&A section of WebEx, that's in the lower right-hand corner. Send that into the host, which I'll see those, and then at the end of his presentation, we'll cover all the questions that are submitted. Outside of that, I guess, Pat, it's up for you now. Take it away, man.
Excellent. Well, thank you, gentlemen. Thank you, Bennett, for the introduction, and appreciate everybody for allowing us to do this and allowing me to do it. I'm happy to do it, and I'm excited to talk about it. So before we really dive into this, right, let's talk about what it is we're going to talk about, right? So the principles of non-Newtonian rheology and the characteristics of extreme shear rates. Okay, so this presentation is all about the way that non-Newtonian or molten plastic flows, particularly through the flow channels of an injection mold. So these behaviors and these characteristics are responsible for a lot of the reasoning behind why we process the way we process, or generally just why the plastics industry does the things that they do for the reasons that they do. So what does rheology mean? Well, rheology is one of those fancier words for the study of a certain type of fluid flow, right? Or in this case, fluids that flow in a laminar type fashion that don't necessarily adhere to the typical Newtonian classical fluid dynamics and all those characteristics. So a large portion of this conversation we're going to have today is about those principles and how this works. And then we're going to talk a little bit about what happens to those principles and those characteristics after we expose them to extremely high shear rates. So those extremely high shear rates and flow rates and pressures are things that we see at MTD multiple times on a daily basis. And we're constantly surprised at the behavior and how it differs from how you're typically going to expect a non-Newtonian fluid to behave. So the first part of this conversation is going to be kind of a general education. So for those of us that want to have a better understanding on kind of the basics of plastic fluid flow, we'll get on the same page with that. And I want to give you guys the right tools so that you can think critically about how shear rates are, or how these fluids are supposed to respond to shear rates and pressures and temperatures and things like that. So with that being said, a little bit more about our company, right? So this is an aerial shot of our facility located in Charlton, Massachusetts. That's central Massachusetts, not too far from the Worcester area. For those of you that are more familiar with that area. You can see here in the back, we've just added about a 12,000 square foot addition that's going to about double our clean room molding space ultimately. So we're really excited about that. So, you know, a lot of work that's gone into this facility in the last year or so, or probably more than that, 2 years, I suppose, new parking lots and new equipment and all kinds of exciting things going on. So the company was established in 1972, so we've been around for about 48 years in the miniaturization world. Started out as a tooling company, building tools and molds, inserts, and then we've kind of grown from that personality to a greater personality that now includes manufacturing and inspection and sometimes even packaging. So yeah, with that addition, we now encompass about 27,500 square feet at the facility. And kind of our personality, right? Our identity here in this industry, we're 100% medical, we're 100% micro right now. So we kind of pride ourselves on taking on projects that are extremely difficult, right? So as we can see on this little pie chart here, about 20% of the projects that we take on are what we call rescues or failed attempts from other suppliers, right? From other contract manufacturers that have tried to make a medical device company's components and have run into some kind of show-stopping issue. So a lot of parts and designs that we get through the door, most people consider to be impossible or near impossible. So in addition to that, another 30% of most of the projects that we bring on are absolute no quotes. They haven't even been attempted from anybody else. So that kind of doubles down on the attitude of, what's impossible. MTD wants to think about what's impossible and what's really possible and constantly kind of push those limits. So along with that attitude, about 10%, if not a little bit more here and there, is committed of our annual revenue towards research and development. So, and of course, that's what I do. I am MTD's research and development engineer. So we take somewhere around 10% of our annual revenue and we commit it towards understanding these unique phenomena that we constantly see in the micromolding space, whether that be rheology and flow related, or something like crystallization related, or heat, all these interactions. There's all kinds of things in this engineering space that don't behave the way we would expect them to. But that doesn't stop us. That gives us an energy and an ambition to understand those unique behaviors so that we can either control them or harness them to our benefit. Right? So another thing about the company, when it comes to micromolding, it seems like a lot of people have their own idea or their own definition of micromolding. People often define what is micro in different ways. So for us, Typically, we've been known to stray from some of these rules from time to time, but typically our parts fit within a 1-inch by 1-inch square box, and anything larger than that, and it starts to no longer fit our micro definition. So these are some examples. Some of these parts are some examples that we've had great success with in the past. And I just wanted to put this in here to give you guys an idea of our label of miniaturization, right? So relative to a penny on here, or relative to a postage stamp here. This part's on a row of pencils. This is a sewing needle, right? So we really, really push the limits of what is possible, even through just our micro features. A lot of these parts we need a microscope to even analyze or see, right? So something that allows us that kind of capability is certainly all of the injection molding presses that we have at MTD, save for one, is our Sodicks. So all of them include this V-line injection unit, right? So this is a picture of one of our molding cells. They're all 20-ton molding machines, and we have a V-line injection unit. So here we can see this area is where the injection unit exists on the machine. Here's the hopper, so they're all hopper fed. We dry on a hopper here and then feed into a system of barrels that differ from a conventional inline reciprocating screw injection unit. So to kind of help you guys understand what these look like or how they behave, this is what our typical injection unit kind of looks like, right? So our hopper would sit in this area here, and we'd feed our polymer resin pellets down into this first heated barrel area. So this heated barrel area contains a screw, not any different or much different than a typical injection molding screw, where we have our certain regions, our melting and our mixing regions, our metering zones, those kinds of things, except for a big difference here is that this screw doesn't actually reciprocate. So there's no check ring to seal off against or anything like that. It doesn't move back and forth like an inline unit does. Instead, it will it acts more like an extruder than it does an injection molding unit, where it will melt, mix, and convey the material through the system, and then only move forward just a little bit to seal off after it's done conveying. So it will convey down into this next region, right? This region down here is another heated barrel zone that contains a reservoir and a plunger. Okay, and that looks something like this. Here's kind of a transparent view of what I'm talking about. So this extruding screw will convey, melt, mix the material through this junction area. Sometimes we call this a touch cap. And then after that phase has finished, the screw will advance forward to seal off here, so that this acts as our check ring instead of actually having a check valve or a shutoff valve. It extrudes the material down into a reservoir where this plunger will advance forward to shoot the shot into our mold. So a big advantage to this, and why I point this technology out, is because there's no check ring, there's no longer any minute backflow, right? Because as a reciprocating screw would advance forward, that check ring takes a little bit of travel time to seal off. And during that travel time, you can have certain levels of backflow with your molten material. Well, when you get down to the scale that we're at, where we need microscopes to see our part, or the part that we're producing might be the part that we're producing might be 0.01% of our overall shot. Small variations from shot to shot because of backflow over the check valve can become really problematic. And things can become really inconsistent very quickly. So for this system to exist and operate the way that it does helps us with our repeatability a tremendous amount. Okay, so again, for those of us that are a little bit unfamiliar with the more technical sides or the specifics of how injection molding works, the next two slides I just want to spend a little bit of time on so that we're all on the same sheet of music. Okay, so after the plunger advances through the nozzle and into our injection mold now, it fills a flow path that looks like this, called the sprue, the main runner, and sometimes the secondary runner systems, right? Enters through the gate, and then these gray blocks represent what the product that we're molding might, where that would exist, right? So that's where the product is in the shot. But all of the conversation that we're going to have today takes place in these red, orange, and yellow flow channels, right? So this is what comes out of the mold after it opens up. So these are the flow channels, or maybe the pipes that the molten resin would flow through to get to the part cavity. Okay. So again, before we get to viscosity and fluid dynamics, there's something really important about polymers that we have to understand, and that is entanglement, right? So for those of us less technical, a polymer is just another word for plastic, right? Where poly means many and mer meaning unit. So in this case, a polymer is made up by many units or molecules that bond or chain together, right, to form these long molecules with these large aspect ratios. Okay, so when they're in the molten state, you introduce heat energy and they disassociate, and then they kind of lay together like cooked spaghetti. Okay, so you can imagine if you were to begin to push that cooked spaghetti, they might get tangled up or knotted up. And the more entanglement there is, the more resistance to flow there is. Okay, which resistance to flow is how you define viscosity. Okay, so that's just it. Viscosity is the resistance to flow, and there are typically two different types of fluids, right? High viscosity fluids that flow, that are thick, and they flow much like honey, or maybe what would come out of the end of a hot glue gun. And then, of course, low viscosity fluids that would behave more like something like water. Okay, but when it comes to plastics and the entanglement of the polymer chains, the viscosity, or the resistance to flow, that molten state will produce is actually dependent and will vary on it'll vary on the environment that it's in, right? Typically, the harder you push them, the easier they'll flow. Now, why does that behavior exist the way that it does? Well, there's two primary factors, right, that go into this, and it's temperature and shear rate. Both of those play a big role in affecting the polymer's entanglement. Okay, so the first one is temperature. So this is the easier of the two, right? As things heat up, they expand. During this expansion, pockets of space form, often called free volume, in between the polymer chains, and that simply allows those polymer chains to flow past each other more easily. Okay, so there was one analogy that we used to use in college that always kind of made me laugh, where we'd say, well, imagine if we all went out in a long, thin hallway and we were all holding 2x4s, right? And we all were told to run down to the end of the hallway as fast as we could, all at the same time. And we did that with no organization whatsoever, and we were all too closely packed together. Well, our 2x4s would kind of run into each other, and before you know it, it would take us longer to get down the hallway than we might expect, right? So rather than giving ourselves some distance, that's what free volume does. That's what temperature does, right? As things heat up, they expand, and they allow individual polymer chains more room to flow down the flow chain. Okay, so to describe shear rate and what the advantages of shear rate give us, that can get a little bit more complicated. So the next thing I want to cover, the next tool in our toolbox to understand, is laminar flow and how that relates to something called turbulent flow. Okay, so laminar flow describes the characteristics of a material that flow in layers. Okay, so a non-Newtonian fluid, like plastics, typically flow in this manner, right? So like this diagram, figure A here, you can imagine cars on a highway, right? Now, if each car represents an individual polymer chain, then they might be going down a certain lane on their highway, and that car won't change lanes, okay? And for reasons that we'll discuss in a little bit, the center lanes tend to drive the fastest, and the lanes that are closest to the flow channel walls drive a little bit slower with their speed, okay? So if we contrast this with something called turbulent flow, this is the type of flow that Newtonian fluids demonstrate, right? Like water, okay? It's much more chaotic. So you can imagine the same cars on the highway, except for this time, they're all trying to go the same speed, and they're all switching lanes very quickly, okay? So to help understand this a little bit more, we have a visual aid here, right? So in this model, in this demonstration, we assume zero velocity at the mold walls, and these arrows, the longer they are, that represents these little particles flowing at a faster rate than shorter arrows. So if we compare that to turbulent flow, now we see that all these little particles are kind of chaotic, and each layer is trying to travel at the same speed that the last layer has. Okay, so now that we've talked about the difference between laminar flow and turbulent flow, we can talk about the benefits of shear rate. So shear rate and its benefit has everything to do with orientation. Okay, and orientation occurs because of frictional drag influences on the polymer chain. Okay, so as something flows through the flow channel, the polymer chains that are closest to the wall will tend to drag on the polymer wall, or on the, excuse me, on the mold wall, because there is resistance, because it's rubbing up against something that's stationary, essentially, right? However, the laminates, because we're no longer changing lanes, the polymers that are in the center layers, the center laminates, don't experience as much frictional drag. Therefore, their velocities can go faster. Okay, so this differential in velocities from the center of the flow channel to the outsides of the flow channel. If you have, like in this example, right, if we have a polymer chain that is perpendicular to the mold walls and then influence faster velocities near the center of the flow channel versus the outside of the flow channel, they will all tend to orient in the direction of flow. So if we go back to our analogy where we're all standing in the hallway with our 2x4s, and we want to make it to the hallway as fast as we possibly can, it might benefit us a little bit to all decide first that we're going to hold our 2x4s all in the same direction over our shoulders, and then we're going to run. That way we won't interfere with each other. Okay, and we can end up inevitably getting down the hallway with a lesser amount of resistance, and we will probably get to the end of the hallway faster, right? So we'll flow easier. So because of these two dynamics, temperature and shear rate, if we introduce both of those, we can lower the viscosity of a non-Newtonian fluid, right? Because we'll increase the space between the polymer chains, and then we'll all make them face the same direction so that they may flow kind of in harmony, if you want to think about it like this. So fountain flow is a concept that describes the way that these fluids travel down the channel, right? And it also describes what the flow front looks like. So the flow front is just the very front of, the polymers, or the molten state that is filling the channel, right? And what the shape of that looks like. So in fountain flow, if you can imagine a polymer chain traveling down one of these center laminates, once it gets to the top, it will tend to roll to the left or the right to the outside laminate. So the dynamics of fountain flow are made up of three main regions, right? The outer laminates, the inner laminates that experience the lowest amount of shear, therefore the lowest level of orientation, but they experience the highest speed or the highest degree of velocity because they experience a lesser amount of frictional drag. Okay, the outer laminates tend to have lower speeds because they experience more frictional drag, yet higher orientation for the same reason. Okay, and then there's a third region called the frozen layer. The frozen layer is actually a stationary layer that just kind of lays down and stays there. And the reason why that happens is because the steel that makes up the flow channel, the steel of the mold, is very cold relative to the temperature of our molten plastics. So as the outside frozen layer of the polymer comes in contact with that tool steel, the tool steel will suck all the heat out of it right away. And it will actually freeze and solidify, right? So that will become important in a couple concepts that we talk about near the end here. Okay, so when we experience ultra high shear rates, when we take these flow rates we take these flow channels and we make them super small, like in our molds and the parts even the part geometries that we make, right? That frictional drag that is experienced through shear rate tends to skyrocket, goes very, very high. Okay. Now, typically, like I said earlier, in non-Newtonian fluids, the harder you push them, the easier they flow for the principles we've talked about. And when that occurs, you'll get something that sometimes we call plug flow that is loosely represented by this top picture here, right? Because of that fountain flow dynamic. However, when we get to ultra high shear rates, sometimes we experience a phenomenon that MTD is dubbed instead of plug flow as tunnel flow, right? And it is characterized by kind of a tubular geometry. So if we were to stop the flow down the middle of the flow channel all at once and then cut it in half, this is the shape that it would typically have versus this is the shape that we end up seeing at ultra high shear rates. So we've characterized that as tunnel flow. Okay, and it is thought to be the result of extreme orientation, where a few things happen. First of all, we think that the laminar velocities nearly equalize. Okay, so back in our examples in the video, right, where we saw that the center lane is driving faster than the outside lanes. Now all those lanes are trying to drive just as fast as the lanes beside them, right? So now a lot of the benefits that we receive from faster laminates than others start to go away, right? But there's still an influence from shear, right? So to better explain this, this is something in the industry that we call the velocity and shear profiles, right? So just like before, these arrows, the longer they are, the faster that laminate is traveling, okay, in this velocity side. And on the right side, we have the shear rate profile, where the longer the arrows are, the higher the shear rate is, the higher the frictional force, the higher the frictional drag is, okay? So if all of these velocities and the velocity profile tend to be the same length and the same speed, but we know that the shear rate is still highest closest to the mold walls, or nearly closest to the mold walls, right? Because out here we have the frozen layer, so there's no shear or velocity going on right against the mold wall. Then we have extra orientation, extra frictional heating, those types of things going on in these areas. So as we start to recognize this tunnel flow phenomenon, it starts to look an awful lot like that shear rate profile, doesn't it? So why hasn't this characteristic been seen more often, right? And in larger parts or larger flow channels, that kind of thing. Well, it has everything to do with something called the second Newtonian plateau. The tunnel flow phenomena occurs in the region of the second Newtonian plateau. So this is another plot that I'm sure many of us are familiar with, viscosity versus shear rate, right? And it describes a concept that we've been talking about, right? The harder we push a non-Newtonian fluid, the easier it flows, okay? So the first region is the first Newtonian plateau, and this is a region with low shear rates and low velocities, right? Where we don't have a lot of influence from orientation or free volume, and the entanglement is very high. So we don't see a lot of drop in resistance to flow at lower shear rates because we're not pushing it very hard at all. Then we move to the transition zone, right? This is the region where non-Newtonians start to shear thin. Okay, shear thinning is just the concept that results in a drop in velocity because of the reasons we've discussed. Okay, so most of the injection molding industry exists somewhere in this transitional zone. Okay, because the flow channels are large enough to allow us advantages to shear thin, but we haven't maximized or reached the limit of that shear thinning. So once we get into astronomical levels of shear rates that we might see in micromolding, we end up limiting out that shear thinning characteristic, and we once again plateau off to behave more like a Newtonian fluid would behave, where all of the laminar velocities are basically the same, and the benefits from shear rate are maxed out. Okay, so this region is a region that is greatly understudied. Okay, and it's understudied for a number of reasons, right? It's understudied because a lot of the viscometers that we use in the industry can't replicate those kind of characteristics. They can't replicate velocities at that speed, at channels that small, and shear rates that high. So the way the practical hands-on tools that we use to measure viscosity differ from the characteristics that we see when we expose these things to extremely high injection pressures and shear rates in our injection molding machines. Another area where this hasn't been studied very much is in simulation software, right? Where we have this simulation software that tries to characterize how a cavity might fill based off material characteristics. But the equations that are used in those simulation softwares, or even in other areas, if you were to do the hand calculation, don't account for this behavior and this plot tapering off again or plateauing off again at extreme shear rates. So a lot of these simulation softwares are going to assume that we'll start to shear thin, and then they tend to just keep trending downward. Okay, so we end up with vastly different predictability in simulation or theoretical viscosity models versus what you end up seeing in real life. Okay, and this ends up being really important because it affects the way that we optimize, or that you have to think about your processing parameters. Right, a lot of like if you were to use the viscosity and shear rate curve to find an optimized velocity, right? But that theoretical equation no longer represents how the shear thinning behavior is actually behaving in the real world, then you have to become very creative at determining how you're going to optimize or determine your processing parameters, right? So again, these are some of our parts, right? Look, the aspect ratio of this part, we have to remember things like shear rate are accumulative, right? They're a property that's accumulative. So as it continues to flow through something long and thin like this, it's only going to continue to increase, right? But the shear thinning, the shear rate will continue to increase, but the shear thinning reaches a point where it has reached a limit, right? So this is something that MTD is very interested in. I love studying this kind of stuff, and it's something that is something that we take pride in continuing to understand, and we are very interested and committed to learning more about, controlling it, and hopefully not only helping ourselves and bettering our capabilities here, but helping our customers to produce more and more challenging components and devices as time goes on, right? Because as we continue to study these things, maybe improve those equations, improve the simulation software, find better ways to improve or optimize alternative ways to optimize our processing parameters that are based in scientific data. I think the entire industry as a whole could absolutely benefit from that. So it's something that we love researching, and we continue year in and year out to dedicate ourselves to. So with that, that's the end of the content that I have for you guys, and I'd be happy to take any questions now. Again, thanks for the time slot, Sodick. I appreciate all your guys' help. Love the platform.
Great, Pat. Thank you for that. We had a few questions come in that we can get started on, and if anyone listening out there, continue to send them. I know Pat's happy to answer and help where he can, and maybe if we don't get a good amount of time to answer here, we can follow up with an email to the individuals as well. Okay. Mm-hmm. First question here that came in. The high shear heat is lowering material viscosity, right? So how hot does the resin become at a high shear heat environment? And does the heat damage the resin?
Right, yeah. So, a lot of questions like this, this is something that makes the plastics industry pretty interesting, right? Because questions like this, it kind of depends on what type of polymer that you're using, right? Or that you're working with. So, shear heating actually has a greater effect on a drop in viscosity than just ambient temperature does. So if we have heater bands on our barrel, right, then that will affect our viscosity and the drop in viscosity less than exposing it to shear rate. So as shear rate increases, the response that it has on the heat generated in the melt is actually exponential, right? So the answer is, although vague, it is shear heating or shear rates, especially shear rates, can raise the instantaneous melt temperature of your material by a lot. And that's something that is another thing that's actually hard to measure, right? And it's another realm that is really important for studying this kind of stuff.
Great. This one that came in says, I suspect there has been a part or two that you have found difficult, if not impossible to fill. Okay. What in those cases has proven to be the limiting factor or factors?
Right. Well, I think so. When it comes to finding something that is really difficult to fill, or, something that is, at least for the time being, impossible to fill, some of the limiting factors end up being, I think, equipment or capability, right? Because if we, it would be great if we could just raise like the melt temperature to infinity, right? Until we became, it became easy enough to flow where it could fill or run just like water, but that's just not practical because we'll reach degradation first. So I think limiting factors include stuff like cooling rate, right? Because if you think about an idea where Well, if it just stayed molten and it didn't continue to fill and cool down as it filled the mold, right? Because you have to cool it down to a realistic ejection temperature to demold it, to get it out of the mold and through your automation process or anything like that. So if we envision an idea where we could just keep that resin molten the whole time without cooling it down at all, then when we might be able to fill things that would otherwise be impossible to fill, right? So some of the limitations include equipment or just the circumstances and the nature of the manufacturing process that increase the cooling rate of your shot, right? So that as you pull heat energy out of that, your viscosity is going to raise, right? So things like, everybody wants a fast cycle time in the industry because time is money, right? So as you increase your cycle time, or excuse me, as you decrease your cycle time, you'll end up increasing your cooling rate and freezing that polymer back into a solid state faster, right? So the nature of the manufacturing process and thinking about the characteristics that influence your cooling rate are really the limiting factors.
Awesome. Thanks, Pat. This question here, let's see here. It says, if the simulation software is limited, does MTD have empirical means of modeling that they use for tool design?
Well, we've been known to do that in the past. A lot of the time, we end up only using simulation software for some of the more simpler things that it can do, because the simulation software right now just doesn't, like we've discussed, just doesn't necessarily represent what happens on a micro scale. So sometimes we'll go based off of company knowledge on other projects. Sometimes we'll go off of notebook or spreadsheet calculations that we run ourselves. But that's not something that is unheard of for us to take a viscosity equation, take a viscosity model, and manipulate it based off of studies that we've done so that it better represents what we end up seeing in the press side. Yeah.
It says one of your competitors in the micromolding world utilizes very little runner. Have you also studied the compressibility of the melt in the runner and the dynamics that are required to get the melt to start to flow and then to control it?
Right. Yeah. So that's something that is something that is really important to master when it comes to micromolding, right? Because we've talked about how, we've thought about how our shots or our parts might be only a small fraction of the entire shot size, right? So what you end up doing is sometimes you end up having to optimize the flow through the runner so that you can deliver it into the cavity more effectively. So yeah, shorter runner systems are certainly ideal in some cases because a shorter flow path gives you a lesser shear rate effect, right? So if we're worried about something like degradation due to shear rate or off-gassing or something like that, runner dynamics, flow characteristics play a huge role in that, right? So yeah, we think about that almost every project, I would say.
Wonderful. Next question for you. Is there a limit as to how many cavities you can have in a micromold?
Yeah, well, so typically MTD keeps cavitation pretty low, right? And I guess a big reason for that, right, is because the shot size is relatively small. The barrels themselves are pretty small. So the greater your shot size becomes, then the less homogeneous your mix becomes that is delivered from shot to shot, right? Because we're using almost the entire barrel capacity per shot, right? So we're not limited to like a one cavity mold, but we certainly very rarely, or actually never, do we see something like 32 cavities or 16 or something. Occasionally we might see, 2 or 4, right? But nothing much higher than that.
Wonderful. Does the cross WLF7 constant model account for the second Newtonian plateau?
Well, I'm not, what would you say it was a cross WLF7 model? Is that what you called it?
Yeah.
Yeah, so I'm not familiar with what the 7 model itself represents. We've used cross WLF before to a better effect than some of the more simplistic models. In terms of what the Model 7 in particular is, I'm not sure what the specifics of that model look like, but I can tell you that the Cross WLF itself does do a much better job of predicting the kind of shear rates or the viscosity drops that we end up seeing.
Excellent. We have a question here wondering if you do any overmolding or insert molding in your micromolding.
Yes, we do a lot. We've actually been doing more and more of that as time goes on. So we have 3 vertical machines that are actually almost entirely dedicated to overmolding. So that's something that we're actually interested in. We do it currently, we do it a lot, and we're interested in doing it more.
Did you study shear-induced crystallization with polypropylene? Or at what level of shear rates does this phenomenon occur?
Yeah, so shear-induced crystallization, I actually have an Antec paper about that. A couple years ago, I did I think it was Detroit 2019. I did a talk about flow-induced crystallization. So we've seen it in polypropylene. We've seen it in some bioabsorbables. We've certainly seen it in PEEK. So yes, we've studied that, and we get that almost on a regular basis with the shear rates and the sizes that we mold at. So if you're interested in that paper or that presentation, feel free to shoot me an email on that, and I'd be happy to share it with you.
Excellent. I'm getting a little glare here. I apologize, Patrick.
Okay.
What is the most difficult resin you see in micromolding?
Well, difficult is there's different levels of difficulty, I suppose, right? Like there are some bioabsorbables that have extremely low glass transition temperatures and things like that end up being quite the challenge. Like polydioxanone is a very challenging polymer to run. There are other polymers that are challenging, like fluoropolymers can end up being very challenging because of how corrosive they are, but because of the extended shear rates that we expose our stuff to. Sometimes off-gassing can be more of a problem for polymers that tend to behave like that. High performance polymers like PEEK or PEI that depend heavily, their characteristics depend heavily on their level of crystallinity. You can imagine if you have such a small part surrounded by so much relative tool steel, you'll suck the heat energy out of that immediately. So when it comes to something like crystallization, that's a thermodynamic phase change. So when we suck the heat energy out as fast as we do, sometimes those crystallization phase changes don't have an adequate amount of time to complete. So when we have polymers that are extremely crystalline, or if we have an application that is dependent on that crystallinity, not saying that it's impossible, actually it's far from it, it's very possible, but sometimes we have to be creative to ensure that crystallinity does in fact complete, and then there are other polymers that you might be surprised about, like polycarbonate is a good example of a polymer that is very challenging to fill thin walls with, right? So we have many cards up our sleeve to coerce those materials to make them do what we want them to do and fill the areas that we want them to fill. But those are just a few examples of some of the challenges with some polymers that you would expect to be challenging, and then other ones that you wouldn't expect to be so challenging.
How does the shear-induced crystallization affect flow? It's kind of a follow-up for you.
Yeah. Well, I don't know that I'm not sure that it affects flow in because of course the crystallization takes place after flow, right? So in terms of that characteristic affecting flow, I don't know if it really does much to affect, the filling mechanics of the material, other than it just certainly reaches a shear limit, right? Because those flow-induced characteristics happen at levels on the second Newtonian plateau, at levels where our flow front experiences this tunnel flow phenomena. But in terms of that characteristic making it, any polymer that demonstrates flow-induced crystallinity, I don't think it typically demonstrates any unique challenge to something that might just be amorphous or something like that. It's more an influence on melting point later on, or functionality if the application requires that crystallinity to be present.
Right. How much glass content can you tolerate in a polymer?
Yeah, so we can really fill polymers. Let's say, like a glass filled nylon, that 30% glass filled nylon, that's a very common one. We could fill that. I think we have in the past, but typically it's not necessary to load something to 30% because our cavities are so small. So I think when it comes to additives, we'll see maybe something around 10%, maybe 15%, but there's a lot that's less than 10% as well. But again, it depends on the additives. But for glass-filled fibers or something like that, the other thing to keep in mind with micromolding is how abrasive that stuff is, right? So it's abrasive in the macro environment too, but when our gates are maybe only a few thousandths in diameter or something like that, something abrasive like a glass filled can end up being really damaging to the tool. So when it comes to abrasive fillers, we tend to try to keep that content as low as possible.
Wonderful. Have you used or evaluated the intrinsic viscosity and its relationship to the viscosities you are seeing?
Yeah, actually, we measure intrinsic viscosity in-house. That's something that we use for incoming material as well as release criteria to our customers, like on a regular basis. So something that we see is we usually see some IV loss, right? Because IV ultimately is a derivative of molecular weight, right? So we end up seeing some IV loss, but it's certainly not it's manageable because of our systems, and our stuff is specialized to what we do. So we do see some IV loss, but it's very manageable. It's very marginal. And it's something that we can actually predict, right? So we have enough experience with most of the polymers that we run here where we'll see minimal loss that we can see coming down the road. So it's something that we can anticipate and prepare for.
Wonderful. Here's one we had, as you can imagine, a few people joining us late. And this one wants to know, how do you define micromolding? Is it size of parts or the size of runners?
Right. So typically, everything's subject to variability, but typically right now our parts fit within a 1 by 1 by 1 inch square box. Okay. So if I actually come back to one of my introduction slides here. This is a slide that I threw up at the beginning to just kind of demonstrate our definition of micro, right? So micro features along with just micro size, right? So some things to point out, like this part on the penny, this on a postage stamp, a sewing needle, and a row of pencils. So for us, micro means quite small, right? It's different from just a few inches in diameter or something like that. So micro features are not impossible, and certainly overall size is quite small by our definition of things.
Excellent. How do you control the nozzle tip shot to shot? What type of nozzle tip do you run? That's a good question for you.
Yeah, so most of our nozzle tips, I mean, in terms of controlling nozzle tips, the Sodicks have a means to, mechanically align, so that, we have good interface with the screws. Most of our nozzle tips are standard nozzle tips, but there are other ones that are custom tapered to certain things. And that's one of the advantages that we have to having a top-down structure at MTD, right, where we have a machine shop and a molding tooling shop right next in the same facility, right next to our clean rooms, right? So if we need to modify a sprue, if we want to open up the orifice to, whatever diameter we think is necessary or something like that, we have the capability to do that. But we also manufacture our sprue bushings and that kind of things too. So we really have ultimate customization when it comes to the nozzle tips, and we often tailor our nozzle tips to fit whatever our needs are.
Wonderful. Here's a question on residence time, Pat. It says this must running into a residence time concern on an upcoming project. It's predicted as 14 minutes running on a 1412 configuration. Does MTD follow typical residence time rules for resin manufacturers, or from your experience, can these rules be broken?
Cool. Yeah, so residence time is something that, like a lot of things when it comes to micromolding, right, is something that you have to take sometimes with a grain of salt, right, because what is practical might not be possible, right? So when it comes to residence time, if you're expecting to have a high residence time, there's a few things that you can do to help kind of prevent any excessive degradation, right? One of those things is a higher throughput, of course. So another thing that we see, we have high residence times, but we have small barrel capacities. So sometimes if we just have a small amount of resin that has been cooking for a certain amount of time, it's not surrounded by a massive amount of heat, right? Things like that will help us to prevent degradation due to residence time. Also, sometimes there are ways where you can bank temperatures, where like if you expect that there's going to be excessive downtime, instead of just turning a barrel heat off or something like that, lower it maybe somewhere just around its glass transition temperature so that it doesn't experience excessive degradation if it's going to be there for a long amount of time. But one thing you have to keep in mind, of course, is that the lower your melt viscosity is, the higher your shear rate is going to be, because the viscosity of the material will be higher. So typically, I've noticed that some materials respond to their thermal tolerance a little bit better than other ones. It's kind of one of those things that is kind of a depends question, depending on what kind of resin you're working with and what your throughput is and those kinds of things.
Excellent. With small or micro shop parts, what is your typical target for cushion, or you screw most forward?
That's something that again can be kind of dependent on what the part looks like, or what exactly we're going for. One thing when it comes to our processing parameters is that sometimes we have to optimize them differently than we would in a macro environment, because the principles that you use to optimize something like cushion or hold pressure or injection pressure or something like that can't really be done on a small scale. So cushion is something that is dependent on the circumstances, but usually a few millimeters, somewhere in there.
Perfect. Well, the tunnel flow you see in small parts, it is evident in the larger parts I have molded. Since it is based on a volume flow or time, what is the actual shear you are getting, and isn't that the concept for your tunnel flow?
Yeah. So I know that this, what we've dubbed tunnel flow is researchable to a certain degree, right? It's out there in the industry. It's certainly not something that I think we've only witnessed and only us. But I think, yes, it is absolutely a characteristic of more so of shear, right? Because once you reach the second Newtonian plateau, one very big principle with that is that all of your laminates have basically reached their max velocities, right? So the velocity of the laminates behave more like turbulent flow instead, but we're still not a Newtonian fluid, right? So back here when I brought up the shear profile, right? If we imagine this to be flat, and then this to still have a similar influence as it does at regular flows, then we might have an extra amount of heating here, an extra amount of orientation here, or something like that. So certainly, I think tunnel flow would occur in any scenario where, whether it's a large channel or not, where your laminar velocities in principle are near, if not equal, right? And then your shear rates, this profile won't change to the same degree that this will. So that tunnel flow is certainly more influenced by figure B here, the shear rate profile.
Excellent. Do you monitor and adjust the nozzle orifice size per resin to minimize or optimize shear rates and the inherent variability that occurs between the nozzle and sprue bushing, including tip breakage?
Occasionally, yeah, we'll do that if we see it. We've done orifice diameter changes before. Sometimes they'll land inside the nozzle, you know, because you gotta remember that the shear rate doesn't begin at the sprue bushing, right? It begins in the injection unit, right? So if you're running into some kind of shear rate issues and you can't, say, you know, address the mold for one reason or another, whether it's time sensitive or, you know, restricted due to the runner geometry or something like that, things like changing the nozzle orifice or how they interface with the sprue bushing, or even the land in the sprue bushing or the land in the nozzle, can all help to make quantifiable changes in your shear rate. Yeah, that will be noticeable.
Excellent. Are TPUs a material used at all in micromolding? And if so, are there any specific challenges you have observed?
Yeah, we use TPUs quite a lot, actually. Well, TPUs are, in a way, one of my favorite materials because they're so tailorable, right? You can have a TPU that is primarily a soft block that acts more like a pencil eraser, or you can have a TPU that is primarily a hard block and acts more like a hard hat or a skateboard wheel, right? When it comes to micro molding them, sometimes they can have higher injection pressures, right? Especially the soft block versions of TPU, because the soft block versions end up acting more viscoelastic, right? So the more viscoelastic your material is, the more compressible it is, and suddenly your injection pressures are much higher. So when it comes to filling thin walls or long aspect ratios, that is one of the polymers that might fit into the category of higher pressures required, right? But I think another challenge with TPUs, right, especially the softer ones, or the more soft block you have in your polymer backbone, is that if you require an elevated mold temperature, which micromolding projects do quite a bit because we need to retain that heat within the polymer shot for as long as possible, right, to keep the viscosity low so we can fill our thin features. Like things like soft block TPUs can be kind of challenging because when the mold opens, they're still quite malleable, right? So we have to, you know, use a number of tricks to prevent distortion or shrinkage or voids and things like that. But again, it's not something that we definitely, you know, we see TPUs all the time, and we've had successes with TPUs, so it's not out of the realm of possibility.
Wonderful. Through this, Pat, what is the indication of degradation?
Yeah, so degradation can come about in a lot of different ways. Typically, it comes about in your typical ways, right? Like yellowing of your material or contamination through black specks, or excessive smoking. All of the easy ones. There are other ones that come up in micromolding that are less prominent, right? Some of them include, like we've seen before, where actually interlaminates that experience the highest amount of shear rate end up degrading before like the center of the flow channel does, or even the frozen layer does. So we'll start with micromolding. Sometimes you'll occasionally see degradation come almost in phases, where higher laminates that are exposed to higher shear tend to degrade first. So if we focus on that area, we can spot degradation early, right? And then if you let that continue to go, sometimes you'll get polymers that, you know, begin to like delaminate and things like that because the shear rate is so extreme, right? So it's very interesting because sometimes in micromolding we can see degradation occur within laminates themselves.
Wonderful. Is there a point when shear and heat become destructive to the material?
Certainly, right. That's going to be the case for every polymer all the time, you know. But every polymer is different when it comes to, you know, how shear sensitive they are, you know. And we have a number of tools to determine that here, right? We can run DSC to determine critical temperatures. That's something that we do often. So if we have a material that we're nervous about with that, unfortunately, we don't have a TGA in house. So we can't analyze degradation that way. But if we have a polymer that we're nervous about or unsure about where to run it at, sometimes we'll characterize it through DSC to determine, you know, where the TG is, where the melting point is, and you know, where the crystallizations points are, and then determine our processing temperatures that way. Of course, keeping in mind if we have excessive shear rates in our molds, then is that instantaneous temperature increase going to push us past the point that we're comfortable with, right? So that's something that you have to remain aware of, but it's different for every polymer, of course.
Wonderful. The last question I'm seeing here come in, Pat, maybe we'll give a few more minutes for anyone to catch up. What do injection molders need for specialized equipment for micromolding?
Right. Well, that's a good question. And that question for me varies a lot, right? So sometimes our specialized equipment can include some prototype equipment that might rapidly change our mold temperatures, right? So that we've done things like that before, where we can flash heat or flash cool something to allow it to fill easier, or fill a geometry that would be impossible to fill otherwise. But I think, generally speaking, a lot of the success that we have in our equipment and the relationship between the molds and our machines and things have to come down to our top-down structure, right? So I think a critical, absolutely paramount characteristic of our success at MTD has everything to do with the fact that we build our own molds. We understand how they behave so that we can learn from them and continue to get better at that aspect, right? And then make changes if necessary that won't take a tremendous amount of time or a third party, right? So when it comes to tools and what is necessary to be successful in micromolding, I think really the best tools up here and what ideas you can implement, and having something like a tooling shop or a machine shop here gives us that great benefit.
Excellent. Couple, I guess, questions have come in revolving around copies of the presentation. Is it possible to get copies of the slides? I know that we are offering a copy of the recorded presentation to those who have attended. So.
Sure. Yeah. I mean, my contact information's on the screen there, so feel free to contact me with any kind of content like that, and I'll see if I can accommodate you.
Wonderful. Well, as Bennett mentioned at the beginning, I guess a few more of these webinars coming up. Looks like we're pretty well booked up through the end of the year. Amongst another micromolder and isometric. 2 weeks out, we have Extol doing laser welding, and then we have Sumitomo Chemical and here in December. So I guess with that, I'm seeing no other questions coming in here. So Pat, thank you very much. MTD, thanks for partnering with us on this. On behalf of myself, Len Hampton, Bennett Howard, appreciate everybody joining us today, and have a great afternoon.
Thanks again, everybody.
Yeah, Patrick, thanks so much. I really appreciate it. It was a wonderful presentation. You know, so much interest. You know, the crowd. Thank you, everybody, for all your very engaging questions. There, of course, there's a lot of interest when it comes to micromolding, and certainly MTD is among the best, if not the best, in the industry. Lindsay, man, thank you for helping put all this together. It's great to work with you guys, and thank you again to everybody that joined. Thank you.
Thanks, Len.